These are the notes for AP Calculus on the topic of Hopital's rule. Or sometimes it's actually an alternative spelling that means the same thing. Sometimes it's actually spelled just like hospital. And just like a hospital provides help, that's what L'Hopital's rule does for something different. So in this case, L'Hopital's rule is when you use direct substitution, just like we normally do when we start figuring out a limit, and if we get this indeterminate form of 0 over 0, right? Then what L'Hopital's rule allows you to do is find the derivative of the numerator. That's what's represented by f of x, f prime of x, and the derivative of the denominator, g prime of x, and then substitute in the constant x is approaching, and find the limit that way. Notice here we're not using the quotient rule on this for the derivative. We're treating them as two separate functions here when you're using L'Hopital's rule. So remember from before when we evaluated 0 over 0, what that told us was that there is a hole at x equals, in this case, a, and then we'd need to remove x minus a. So that technique oftentimes worked, well, it did work before, for when you had 0 over 0 to remove the hole. But sometimes it's not easy to remove that just algebraically like we've been doing. So that's where the L'Hopital's rule comes in handy and gives you an alternate way of figuring out the limit. And we didn't do this previously when we went over limits because you guys hadn't learned derivatives yet. But now that you guys know the rules for derivatives, now we can go back to limits and apply L'Hopital's rule. So it says find the limit with and without using L'Hopital's rule and compare your answers to ensure they're the same. So it should give you the same thing both ways. So the first thing, don't skip this initial step. You do need to substitute in what x is approaching, in this case 2. So we'll have 2 squared minus 4 divided by 2 squared plus 4 times 2. So on the numerator, that gives you 4 minus 4 is 0 over, that's 2 squared is 4 plus 8 is 12 minus 12 gives you 0. So that tells you we have a hole at x equals 2, which means we need to remove the factor x minus a. So let's try it without L'Hopital's rule. A review of the way we did this before. So without L'Hopital's rule, then we can use factoring here. The numerator, you can see, factors into difference of perfect squares. X plus 2 and x minus 2. And the denominator, factors of negative 12 to add to be 4 would be positive 6 and negative 2. So I use the shortcut here because the leading coefficient is 1. X plus 6 and x minus 2. And then the x minus 2's can be removed, which is what we wanted. And remember, as soon as you do that, then you can substitute in the 2 for x. So you get 2 plus 2 divided by 2 plus 6 gives you 4 over 8, which reduces to 1/2. Okay, that's the way we figured these out before without L'Hopital's rule. Now let's see how we can use L'Hopital's rule as an alternate way. In this case, it's asking us to use both ways. So with L'Hopital's. All right. So when you get 0 over 0, L'Hopital's rule says you can take the derivative of the numerator and denominator separately. Again, not using the quotient rule, so not to get it mixed up with that. We're not trying to find the derivative of this whole expression. Our goal is to figure out what the limit is. So the derivative of the numerator, you can see, derivative of x squared is 2x. The derivative of negative 4 is 0, constant by itself, divided by derivative of x squared 2x, derivative of 4x 4, derivative of negative 12, 0, And then once you take the derivative of each one separately, then you can substitute in 2, what x is approaching again. That's what a is represented by. So 2 times 2 over 2 times 2 plus 4 gives you 4 over 4 plus 4, 8. So notice again, we get the same answer of 1. So here there's 2 different ways of figuring out this limit. One, using factoring to remove the factor x minus 2 creating a hole, and the other is with the Hopital's rule. All right, now let's take a look at some that are a little bit different here. So let's start by substituting in 1 for x. So we'll have 1 cubed minus 5 times 1 plus 4 in the numerator over 2 times 1 to the 5th plus 7 times 1 squared minus 9. So 1 cubed is 1 plus the 4 gives you 5 minus 5, so that's 0. Over, that's 2 plus 7 is 9 minus 9 is 0. So here, again, we've got a hole at x equals 1, and we could try to remove the x minus 1. But notice, unlike the previous problem, if we tried to do that by factoring, these are not easy to factor with x cubed in x and x to the 5th x squared. What you'd have to end up using is either long polynomial division or synthetic division, and to figure out what the other factor would be when you divide it by x minus 1. So it could be done, but that would be pretty time consuming to figure it out. So here, the Hopital's rule is actually a time saver. It makes it a little easier to find the derivative, and so you don't have to do long or synthetic polynomial division. So if we just take the derivative of the numerator, we get 3x squared, derivative of negative 5x negative 5, derivative of 4 is 0. Divided by, on the denominator, the derivative of 2x to the 5th, which is the power of 10x to the 4th, plus 14x, the derivative of 7x squared, and then that's it. Derivative negative 9 is 0. And then we can substitute in what x is approaching 1, so it'd be 3 times 1 squared minus 5 over 10 times 1 to the 4th plus 14 times 1. So you end up with 3 minus 5, negative 2, over, that's 10 plus 14, 24, which you can reduce to negative 112. So that would be your limit. And notice that's a general limit. That's what it's approaching on both sides, so that's also your left and right hand limit if you're asked about those. So here the Hopital's rule is a big time saver. Alright, let's take a look at the next one. So if we substitute in 3 on this one. Again, don't be tempted to skip this step of substituting, because if you get something that's not 0 over 0, 5 over 0, or just a regular number, 1/3, then the Hopital's rule, if you apply it, it's going to give you the wrong answer. So make sure it's 0 over 0 before you try to apply the Hopital's rule. And substitute 3 in the denominator. So let's see, that's 9 plus 7 is 16, square root of 16 is 4, so 4 minus 4 is 0, over 9 minus 9, 0. So here there's a hole at x equals 3, so we can try to remove x minus 3. So this one could also be done. Remember with a radical you could use the conjugate and multiply the numerator and denominator by the conjugate. That would work. But let's see instead how the Hopital's rule would work. Here it's really an alternate way again. So first thing, since it's a radical, before I apply the Hopital's rule, let's rewrite this as x squared plus 7 to the 1/2 minus 4 over 9 minus x squared. And now let's take the derivative of each one separately. So the derivative of the numerator, notice we've got a function inside, so that's going to require the chain rule. So we'd have 1/2, using the power rule first, x squared plus 7 to the negative 1/2, and derivative negative 4 is 0, so that's it on the numerator. And then times the derivative of the inside, derivative of x squared is 2x. All divided by, derivative of 9 is 0, derivative of negative x squared is negative 2x, using the power rule. And then you could substitute in the 3 right now, but sometimes there's some simplifying you can do that makes it a little easier before you substitute in what x is approaching. So there's different ways to simplify this, actually. This 2 and this 2 can reduce out, or you could reduce this 2 with this 2. Either way is fine. I'm just going to reduce these two so we don't have this little fraction we have to worry about. And then notice the x's reduce out as well. And then you can bring this with a negative exponent to the denominator. So this would simplify. That means all that's left on the numerator is just 1. Everything else reduced out. And we still have this negative 2 on the denominator. And then putting that in a radical form would be the square root of x squared plus 7. And then it's much easier to substitute in the 3 now than if we tried to substitute it right here. So we'll just have 1 over negative 2 times square root of 3 squared plus 7. So 1 over negative 2. Square root of that's 9 plus 7 is 16, which is 4. Gives you negative 1/8. And that's the same answer you would have gotten if you'd used the conjugate here. So again, so far it looks like the Hopital's rule is just an alternate method. So you might wonder, well, why do we need it if there's other ways of going about it? Well, sometimes it's an alternate method, like on these problems. Sometimes it's the only way of figuring it out. So on this one, notice if we substitute in 2, we'll get 2 squared. Oops, and then we substitute 2 for the x there, so it becomes, you could write pi 2, I guess, but we usually write it as 2 pi. Divided by 3 times 2 cubed. Minus 12 times 2. So remember, sine of 2 pi. 2 pi is the same place as 0 over here. Sine is the y coordinate, so that's 0. So sine of 2 pi is 0, that wipes out the whole numerator, gives you 0. And on the denominator, you can see we've got 2 cubed is 8 times 3 is 24, minus 12 times 2 is 24, 24 minus 24, also 0. So this graph does have a hole at x equals 2. But if we try to remove x minus 2, you can do that with the denominator by factoring. But look at the numerator. You're not going to be able to remove an x minus 2 when there's a trig function there, sine. There's no way we're getting x minus 2 out of that using algebra. So here's where the Hopital's rule is necessary. And chances are you'll see at least one on the AP test where it is, so that they can test to see if you actually know how to use the Hopital's rule and not just the other methods that we've gone over. So when we take the derivative of the numerator, notice this one's a little more complicated because we've got x squared times the sine of pi x. So when you take the derivative of that, it's going to require the product rule. And also, because we've got pi x inside of sine, it's going to require the chain rule. So product and chain there. So the first one I'm treating as x squared times the second one sine of pi x. So using the pattern for the product rule overall, the derivative of x squared is 2x times the second one sine of pi x as it is, plus x squared as it is, times the derivative of sine. That's where we're using the chain rule. So the derivative of sine on the outside is cosine. Pi x stays inside there. And then the derivative of pi x, using the chain rule, you have to multiply by that, is just pi, just like the derivative of 3x would be 3. And now let's take the derivative of the denominator separately again. We're not using the quotient rule here. So the derivative of the denominator is a simple one there. It's just 3 times 3, so 9x squared minus 12. And then we can go ahead and substitute in what x is approaching 2. So we'll have 2 times 2 times the sine of 2 pi plus 2 squared cosine of 2 pi times pi. All divided by 9 times 2 squared minus 12. Alright, so sine of 2 pi we already established is 0. So notice that wipes out this entire first term here. But cosine of 2 pi is the x-coordinate 1. So that's just going to be 1 times 2 squared is 4 times pi. So that just gives you 4 pi. Over 4 times, 2 squared is 4 times 9 is 36 minus 12 is 24. And you can reduce that to pi over 6. So here's what, again, when we had these L'Hopital's, we'll figure out because we're moving this x minus 2 is not going to happen on the numerator. Alright, let's take a look at another one where something a little bit different happens on this one. So start off again by substituting 0. What x is approaching 0 for x, so 0 squared minus 3 times 0 plus 3 times the sine of 0 divided by 1 minus the cosine of 0. So again, 0 is the same place as 2 pi that we just saw there. So right there, you can see sine of 0 is the y-coordinate 0, so that wipes that out. So that's 0, all these terms are 0, so we get 0 in the numerator. And cosine of 0 is 1, so that's 1 minus 1 gives you 0 on the denominator. So this time we have a whole at x equals 0, which would normally mean we need to remove x. But here that's not going to happen on the numerator or denominator because of the trig functions. So again, we need to use L'Hopital's rule on this. So when we take the derivative of the numerator, derivative of x squared is 2x, derivative of negative 3x, negative 3, plus 3, the derivative of sine x is cosine x, so the 3 just stays out in front. And on the denominator, the derivative of 1 is 0. The derivative of cosine is negative sine, so the negatives cancel out and give you just just sine x on the denominator. And now we can substitute in 0. So we get 2 times 0 minus 3 plus 3 times the cosine of 0 divided by the sine of 0. But again, cosine of 0 we found is 1 here. So that becomes 3 minus 3 is 0, and that's just 0. So we get 0 on the numerator. Sine of 0 is the y-coordinate 0. So we still got 0 over 0. So first you might think, well, I guess L'Hopital's rule didn't work on this one. Well, it didn't work, but it didn't work yet. So it still can work. It's just they have to do a little more work here. So if you get 0 over 0, all that's telling it's not giving you what the limit is yet. So you just have to use L'Hopital's rule again. So if you keep using L'Hopital's rule, keep taking the derivative of the numerator and denominator separately, eventually that's going to give you what the limit is equal to. So you just have to keep at it until you don't get 0 over 0 to find the limit. So the derivative of 2x is 2, derivative of negative 3 is 0, derivative of cosine is negative sine, so it becomes minus 3, and negative 3 then sine x, and the derivative of sine is cosine. So then if we substitute in the 0, we'll get 2 minus 3 times sine of 0 over cosine of 0. So again, sine of 0 is 0, so that wipes that term out. So we just are left with 2 on the numerator over cosine of 0 is the x-coordinate there, 1. So now we got what the limit equals. It equals 2. So we just had to use L'Hopital's rule twice here instead of just once. Sometimes you might have to use it 3 times, 4 times, it just depends on the problem. But eventually, you won't get 0 over 0, you'll get what your answer for the limit is. All right, let's take a look at a couple more here. On this one here, if we substitute in pi, and remember this cubed means the whole cosine is being cubed. So it'll be cosine of pi over 2 cubed divided by sine of, here when you plug in pi, it's sine of 2 pi. So pi over 2 is right here. And remember cosine is the x-coordinate, which is 0. So 0 cubed just gives you 0. And then the sine of 2 pi, again 2 pi is the same place as 0. Sine is the y-coordinate there, so that's 0. So you do get 0 over 0, and again this is one with the trig functions where you have to use L'Hopital's rule. Just like on the previous one, we weren't able to remove the x. On this one, you would have, there's a hole at x equals pi here. So you'd have to try to remove x minus pi. And you can see there's no way we're getting x minus pi out of the numerator and denominator. So we've got to use L'Hopital's rule. Alright, so let's rewrite this numerator here first so it's easier to take the derivative of. Remember we said the whole thing is cubed there. And then we've got cosine inside of that. And inside of cosine we've got x over 2. But rather than write as x over 2, because then it looks like you need to use the quotient rule on that. It's the same thing as just pulling the constant out in front as 1/2 x. And on the denominator, we've got sine, and they didn't put the parentheses here, but it's really like that. So sine of 2x. So when you use the Hopital's rule, notice on the numerator we've got two functions inside. Cosine inside the cubed, 1/2 x inside cosine, so this numerator is going to be the double chain rule. And on the denominator, it's just got one function inside, so it's going to just be the regular chain rule. So here on the numerator, the power rule first, so bring down the 3. So it'll be 3, the function side stays the same. Cosine 1/2 x squared, reduce the exponent by 1. Then we multiply by the derivative of cosine, which is negative sine. The function side 1/2 x stays the same. And then finally multiply by the derivative of 1/2 x is 1/2. Divided by the derivative of the denominator, just the single chain rule, derivative of sine is cosine, 2x stays inside there. And then times the derivative of the function side, derivative of 2x is 2. Alright, so now we can substitute in the pi, what x is approaching, in for all the x's. So I'm just going to simplify this a little bit here, and as we do that, and pull everything that's a constant out in front. So we've got a negative, a 1/2, and a 3. Multiply those together gives you negative 3/2 out in front. And then we'll have cosine of pi over 2 squared times the sine of pi over 2. And divided by 2 times the cosine of 2 pi. Let me plug in pi there. So on the numerator, notice cosine of pi over 2, remember that's the x coordinate there, that's 0. So that 0 there wipes out the entire numerator, so we get 0. But on the denominator, you get cosine of 2 pi is 1. 1 times 2 is 2. So notice it's not 0 over 0, it's 0 divided by 2, which is just 0. So that is what our limit is equal to 0. So we didn't have to use the Hopital's rule a second time here because it wasn't 0 over 0, it was just 0 over 2, which is 0. So that just means there's a hole at pi, and on both sides of pi it's approaching a y-coordinate of 0 from the left and the right, because it's the general limit. Alright, let's look at one more. So take first substitute in the 0. So 1 minus 3 times cosine of 0 divided by, remember this really means sine is being squared, so sine of 0 squared. Well, cosine of 0, again, is 0 is the same place as pi, 2 pi here. So that's cosine is 1. So that's 1 minus 3 is negative 2 over sine of 0 is the y-coordinate there, 0. So notice we didn't get 0 over 0. So the first thing, you don't get 0, 0, do not use the Hopital's rule. If you do, it's going to give you the wrong answer because it's not 0 over 0. So that's why it's important to substitute in first to see if you even can use the Hopital's rule. Plus, notice this is not a hole. When you have a number that's not 0 over 0, when it's undefined like that, remember what that actually indicates, it's a vertical asymptote at x equals 0. So a little review here, when you have a vertical asymptote, and this is asking about the general limit. Then remember you just have to test from the left and the right because there's two possibilities. It could either be up to infinity or down to negative infinity on each side. So you can start with either one. Let's say we start from the left. So the limit as x approaches 0 from the left, and I'll just call this whole thing, so I don't have to write it down again, f of x. So of f of x equals, remember on the numerator we used the sign from right here, which was a negative 2, so it'd be negative, over The denominator, we would normally substitute something a little bit less than 0, like -1, or in this case it's a trig function, you could use like -pi/2. But here, notice you don't actually have to because of the squared. Because of the square, we know the denominator, no matter what we substitute in there, other than something that's going to make it 0, is going to be positive. So a negative divided by a positive, that means it's going to be approaching negative infinity from the left, like that. And then the limit as x approaches 0 from the right, again on the numerator, we're just going to use the sign from the -2, okay. Negative. And same thing on the denominator, because it's squared, even if we plug something a little bigger than 0, like pi/2, it gets squared, so it's going to be positive. So because of that, negative divided by positive, also a negative infinity. So remember, when the left and right limits are the same, then that is your general limit. In this case, negative infinity. If they were different, then remember it would be does not exist. And that concludes the notes for AP Calculus on the topic of the Hopital's rule.